Okay, so we'll pick up with section 4.1 and 4.2. It says the graph is symmetric to the x-axis if it contains both xy and x negative y. So as an example, let's look at x equals 1 minus y squared. I'm going to use the table backwards from how I'm used to because this equation has been solved for x and not y. So if y is 0, x is 1, 1, 0 is on the graph. If y is 1, 1 minus 1 is 0, x is 0, 0, 1 is on the graph. If x is negative 1, 1 minus 1 is 0, x is 0, 0, negative 1 is on the graph. If x is 2, 2, negative 3 is on the graph. 1 minus 4 is negative 3. And if x is negative 2, 1 minus 4 is negative 3. Negative 3, negative 2 is on the graph. So this graph is symmetric to the x-axis. It contains both the points x, y, and x negative y on it. And you can see that if you spin the graph about the x-axis, you'll get the same picture on the graph. Okay, so in the next example, a graph is symmetric to the y-axis if it contains both xy and negative xy on it. I can use the table like normal here for these next two problems because the graph is symmetric to the equation has been solved for y and not x. Y is equal to x to the fourth minus 2x squared. If x is 0, y is 0, so 0, 0 is on the graph. If x is 1, 1 minus 2 is negative 1. Here's 1, negative 1. If x is negative 1, 1 minus 2 is negative 1. Negative 1, negative 1 is on the graph. If x is 2, 2 to the fourth is 16. Minus 8 is 8. Okay, so I don't have it scaled that far, but I'd want to make sure 2, 8 is on the graph. And if x is negative 2, negative 8 would be on the graph. Okay, so negative 2, 8 on the other side would be on the graph. Again, I don't have that scaled that far, but as a note, the end behavior, and there's 3 turning points on this graph. There's a degree 4 polynomial. So there'd be 3 turning points. Here's 1, 2, 3. And the end behavior, there's a 1 in front of x squared, x to the fourth, and it's x to the fourth. So it's going to open up on both ends. Okay, and this graph is symmetric to the y-axis. In other words, if I spin the graph about the y-axis, I get the same picture. For any point that's on the graph, xy, negative xy is on the graph. And I can see that. So 1, negative 1 is on the graph, negative 1, negative 1 is on the graph. Negative xy is on the graph. Okay. Definition, a graph is symmetric to the origin if it contains both xy and negative x, negative y on it. So for example, suppose that y is equal to x cubed minus 3x. Well, I can use the table like I normally would here, selecting x values and coming up with some corresponding y values. So if x is 0, y is 0. If x is 1, 1 minus 3 is negative 2. If x is negative 1, negative 1 cubed is negative 1, plus 3 is 2. If x is 2, 2 to the a cubed is 8, minus 6 is 2, so 2, 2 is on the graph. And if x is negative 2, negative 2 cubed is negative 8, plus 6 is negative 2. So this graph would be symmetric to the origin. At any point that I tell you, x, y, negative x, negative y would be on the graph. Okay, and here's a point, 2, 2, negative 2 is on the graph. 1, negative 2 is on the graph, negative 1, 2 is on the graph. Okay? And this is a degree 3 polynomial, so there'd be at most 2 turns, and we open down on the left and up on the right. Okay? Let's let f be a function. Then if f of negative x is equal to f of x for all x, then f is an even function. And if f is symmetry of the y-axis. If f of negative x is equal to negative f of x for all x, then f is called an odd function. An odd function is always symmetric to the origin. Okay, why not symmetry? Why didn't I say anything about symmetry to the x-axis here in this definition? Well, because f is a function. And if you have a function, okay, the graph won't be symmetric to the x-axis. Otherwise, it failed the vertical line test. So I can't use function notation here. Okay? So that'd be the problem. Is that you're only going to test for any symmetry to the y-axis or to the origin. Okay, here's an example. Suppose in these examples I determine if the function is even or odd, and then what kind of symmetry there is, and then at most how many turning points there are, and then what happens on both ends. Okay, so for example, suppose that f of x is equal to 5x to the fourth minus 3x squared plus 1. You always start off with f of negative x. Okay, that's what we see there. So f of negative x to the fourth is x to the fourth, negative x squared is x squared. So 5x to the fourth minus 3x squared plus 1, well, that's exactly what I have initially, so that's equal to f of x. F of negative x is equal to f of x for all x, so I call that an even function. An even function is always symmetric to the y-axis. So I can spin this graph about the y-axis, and I would get exactly the same picture. There would be at most 3 turning points. Okay, so I get a degree 4 polynomial. And I'm going to open up on both ends because there's a 5 in front of x to the fourth. 5 is greater than 0. Okay. Next example, g of x is equal to x squared minus 4x cubed. So I always start off with g of negative x. F of negative x. Okay, here, g of negative x is negative x cubed minus 4 times negative x squared minus 4 times negative x cubed. Negative x squared is the same as x squared. Negative x cubed is the same as x cubed. So I've got x squared minus 4x cubed. That's not the same as g of x. Okay, I've got a plus sign, and that should be a minus sign. Negative g of x is what I need to find next. Negative g of x means negative the whole thing. X squared minus 4x cubed. And when I distribute the negative there, negative x squared plus 4x cubed, that's not the same as g of negative x, excuse me, and because I've got a negative sign instead of a positive sign. Not the same as g of negative x. So negative g of x is not the same as g of negative x. This is neither even or odd. So there's no symmetry for a function that's neither even or odd. There is at most 2 turning points because I've got a degree 3 polynomial. There'd be at most 2 turns. And you're going to open up on the left and down on the right. Up on the left and down on the right. Okay? The next example, h of x equals 5x cubed minus x. Okay, h of negative x is the same as 5 times negative x cubed minus negative x. Negative x cubed is the same as negative x cubed, and I've got the, and I'm subtracting negative x, so negative 5x cubed plus x. And that's not the same as h of negative x, h of x, sorry, because I've got a negative, the signs are different there. However, negative h of x is the same as negative the whole thing, 5x cubed minus x. Well, negative the whole thing, 5x cubed minus x, that'd be negative 5x cubed plus x. And these are the same. Okay, so h of negative x, that's what that is the same as negative h of x. And that indicates an odd function. An odd function is always symmetric to the origin. And at most there'd be two terms, since I've got a degree 3 polynomial. And there'd be a positive number in front of the degree 3 term. So you're going to open down on the left and up on the right. Okay. There's a little bit with piecewise functions in this section, and why they're coming back to it again is because previously when we looked at piecewise functions, we only looked at ones that involve lines. Okay, so now that we've gone deeper into the material, they bring it up again, and you don't have just lines down now. So suppose that we got f of x equals x cubed plus 1 if x is less than or equal to 1, and 1 minus x squared if x is greater than 1. Okay, y equals x cubed plus 1 means I've got the cube function shifted up 1 unit. Okay, you can use what I know about transformations here. So 0, 0 is going to be at 0, 1. 1, 1 is going to be at 1, 2. And negative 1 is going to be at negative 1, 0. I've got those 3 points plotted. And x is less than or equal to 1. Okay, so anything that's 1 or less needs to be kept. Anything that's bigger than 1 up here, I would need to erase. Okay, piece 1 is now completely done. Piece 2, y equals negative x squared plus 1. I write it like that, negative x squared plus 1, if x is less than, or if x is greater than 1. Negative x squared means that I would flip the graph upside down, and the plus 1 means I'd shift up 1 unit. So I've got a parabola shifted up 1 unit and flipped upside down. Okay, I only want that part of the graph for when x is greater than 1. Okay, well here's 1. 1, negative 3 would be on the graph. 1, negative 3, or 2, negative 3. 1 minus 4 is negative 3. And 2, negative 3 is on the graph. X is strictly greater than 1, so I'd want an open circle there at 1, 0. The domain of this function is all real numbers. In other words, this graph goes downward and outward on both ends. The range of the function is all y values such that y is less than or equal to 2. Okay, and the range, of course, I'm looking at the y-axis and seeing what that covers. Anything that is less than or equal to 2 puts me on the graph. Anything that's bigger than 2 puts me up here, and I don't have any graph up here. F is not continuous at 1. You can see that. In order to draw this graph, I must lift the pencil from the paper. I must do that. That's going to happen 1 time. So F is not continuous at 1. Okay, here's homework problems for the section. Page 269, the problems there are in section 4.1, and then section 4.2 on page 286. Okay.